This is part 2 of Pre-Calculus Notes for Essential Skill B3, Sketching Polynomial Graphs. Here we look at multiplicity. The exponent of a polynomial is called its multiplicity. In example 3, we say that the x minus 1 factor has multiplicity of 2. We say that the x plus 2 factor has multiplicity of 3, and the x minus 4 factor has multiplicity of 1. As we saw in the last example, a factor with a multiplicity of 2 will bounce like a parabola. If a factor has a multiplicity of 3, it will flatten like the center of a cubic. Let's look at an example. First, I'm going to make a list of the zeros. I'm going to annotate this list so that we don't lose track of what the shape of the graph is going to be near these zeros. A power of 2 indicates what we call a double root. Don't worry, we'll abbreviate these later. Now we draw the number line. Again, I'm going to use these annotations to put reminders of what the shape of the graph is going to be. At 1, we have a double root, so I'm going to put a little parabola symbol here. At -2, we have a triple root. I'm going to put this cubic symbol here. We flatten and accelerate. 4 is a single root. That's a linear root. And so I'm just going to put a straight line there. It's important to stay organized because forgetting this shape at the zeros is a very common careless error. Next, I'm going to draw my chart. Next, I'll pick my test numbers. And fill in the easy column. And now I evaluate the positive and negative intervals. -3 plus 2 is -1. -1 cubed is still a negative number. -3 minus 4 is a negative number, and so the leftmost region will be positive. Go ahead and finish the rest of the table. Here's what you should end up with. Positive interval, negative interval, negative interval, positive interval. Now we set up the graph. Now we need to look back up at the number line map and remember that at the -2, 0, we have a cubic shape, a cubic flattening. So here's how that looks. We're going from positive to negative, and so we descend, flatten, and continue. At our 0 of 1, we're going to bounce like a parabola. So we come in, bounce, make sure this is curved like a parabola and not angled. And then our final 0, 4, is a linear factor, and so with no exponent, we pass through like a linear function. The next component we're going to talk about is end behavior of a polynomial graph. Consider this. A polynomial graph can get a little wobbly near the zeros, but eventually it's going to decide what it's going to do. And sometimes we want to concern ourselves with what it's doing when it makes up its mind. So in the middle, a little bit wobbly, but eventually this one's going to be rising on the right side or falling on the left side. We call this end behavior. So this is whether its graph eventually increases toward infinity, because this is headed up towards infinity, or descends toward negative infinity, or stabilizes. Bear in mind that infinity is not a number. We talk about it in the context of limits because with limits we're concerned about the direction that it's headed, not with an actual destination. The way we write this, to look at the right side, we look at what happens as x goes toward infinity. So we are looking at the function line as x goes to the right at the end. What's y doing? Well, y is increasing without bound. And so it's headed toward positive infinity. This is where we write the infinity. This is the limit. Similarly, if x approaches negative infinity, so x is headed to the left, well, once it decides which direction it's going to go, that direction is down. And so this is headed down toward negative infinity. Let's look at an example. This example is also going to show us what to do if there's a minus sign in front. So we'll look at the graph and we're going to ignore this. We are not going to give the minus its own column. That was an idea that I thought was neat last year and it confused everybody, so we're not going to do it. We'll start, as always, by listing the zeros. We have 0 itself from the x factor. We have -3, and we have 5, which is a triple root. We draw the number line. And I'll put markings about regarding the multiplicity. So 5 is the triple, so we're going to have that cubic wobble. 0 and -3 are going to be linear factors, so I'm going to just draw straight lines. Now we draw the table. Notice that we're connecting the minus to the x, just the first factor. Go ahead and pause the video and try this out, and then we'll compare answers. Here are my results. We start with a positive interval, then negative, then positive, then negative. If you got something different, please take a moment and compare answers in the table. Notice that if you pick different x's, that's okay as long as they're within the same intervals. When you have the correct number line map, go ahead and plot the graph. We'll talk about the end behavior in a moment. Here's my solution. First, we put enough tick marks on the x-axis to cover all of the zeros and label them. Next, we plot the zeros themselves. Next, I mark the boundaries of the positive and negative intervals and label them. This is based on the number line: positive, negative, positive, negative. Finally, I fill in the function line. Remember that at x equals 5, we have a triple. We have a cubic shuffle. So positive, negative, positive cubic flattening. Finally, we can look at the end behavior. The limit as x approaches infinity, so this is the right side because x is getting larger and larger, is going to be what the y-coordinate is doing. Well, we know that we are heading negative. Our sign pattern chart told us so. So this is headed toward negative infinity. Similarly, as x heads toward the left, negative infinity, we see what y is doing. It's rising, rising, rising. Y is approaching infinity. We also say that it's increasing without bound. We'll conclude our study of sketching with some important facts. Using this method requires the factored form of the polynomial. The problems you work may not always be in factored form, and so you may need to be factoring it. After skill set B2, you should be able to factor just about anything. This is a quick definition. The highest exponent of a polynomial when it's in standard form is the degree of the polynomial. If the polynomial is in factored form, we can still find the degree by looking at the highest exponent of each factor and consider what the multiplicities will do to that. We'll see an example of that very shortly. The degree of a polynomial is also important because it tells us how bouncy the graph can be. In other words, it's going to tell us how many different directions the graph can go. For example, a third-degree polynomial could go up, then down, then up again, or it could go down, then up, then down again. It doesn't have to go 3 different directions, but it can. A third-degree polynomial could never go 4 directions. The degree limits this. Finally, if a polynomial does not have any x-intercepts, that doesn't mean it doesn't have any zeros. We saw in skill set B2 that we can still have zeros of the polynomial. They just involve I. They are imaginary. Here's an example of finding the degree of a factored form polynomial. We say this is the sum of the highest exponent in each factor with multiplicities. So, in the first factor, the highest exponent is 1, but with a multiplicity of 2. 2 times 1 means this is going to contribute 2 to the degree of the polynomial. Similarly, next to the 1 with a multiplicity of 3 means this is going to contribute 3 to the degree. The highest exponent here is 2, but there's no multiplicity, so this only contributes that 2. We add these to get the degree. This means that the polynomial could have 7 different directions, which means that the direction could change up to 6 times. Remember that these are the maximum possible. Remember, if you want to draw a rough sketch of a polynomial like this is not in factored form. We need it there in order to get the zeros. The next question may require some clarification. When we say the polynomial has no multiplicities, that really means no multiplicities greater than 1. So no double roots, no triple roots. None of that's allowed. Questions 7 and 8 are good ones to think about, so I want to give you some time to work on this yourself and see if you can come up with an answer. This would also be a very good time to work on the problem set a bit. You should have everything you need now in order to sketch all of the graphs. I'll put the answers to 7 and 8, as well as the last page of notes, in the final video.